Welcome, everyone. I'll be talking about TensorFlow NumPy. I'm an engineering manager on the TensorFlow team, and I'll be joined with my colleague Peng Wang as well. We'll talk about how to take NumPy and accelerate it using TensorFlow. So a very high-level summary is that you can take your NumPy code, you can dispatch it to TensorFlow runtime, allowing your code to run faster and also to be able to leverage accelerators like GPUs and TPUs. On top of that, you get all the benefits of the TensorFlow ecosystem. This includes auto differentiation, compiler optimizations like operator fusion and loop auto vectorization, also distributed execution onto clusters and pods of accelerators. You can also use TensorFlow API seamlessly. For example, you can use linear algebra, signal processing, and deep learning APIs of TensorFlow. You can also serialize your code used by a safe model and serve them on clusters of servers or even mobile. So as a NumPy user, this should be an exciting set of new capabilities. However, we believe that this is a value addition for TensorFlow users as well, because NumPy brings in a popular, stable and time-tested API with extensive documentation and even a reference implementation. This API surface is a great fit for a whole class of problems needed for power users and researchers as well, and it should nicely complement the Keras deep learning APIs. Please check out the extensive guide we have put on tensorflow.org to get started. The rest of the talk is structured as follows. So we will briefly talk about how to quickly get started with using this and also go into what is supported versus not. We'll touch upon interoperability with NumPy and TensorFlow and work through some example code. Next, we'll look at how to add new TensorFlow, new NumPy operations. Finally, we'll dive into some case studies of using this API. So the TensorFlow NumPy support is available in a stable version starting from 2.4. So for now, it is available in TF nightly. Once you have installed that, you can start using it by importing the tensorflow.experimental.numpy module. And then after that, you can just start writing regular NumPy code using this module. So the example code here, for example, creates a 2D tensor of random values. It clips it into some range and then does sigmoid computation on the value. This code can run imperatively, and so you can examine the shapes and values that you computed. You can also look at what device this code is being placed on. So if you look at a device property, it shows that the code, the data is already placed on GPU, and the computation has been happening on GPU if you have one available, without having the user to do anything. So that's all great, but how well does this work? Does it run your code faster? We did a simple benchmark for this toy problem of sigmoid computation. So the graph here shows on the x-axis input size, and on the y-axis the time taken to compute sigmoid on an input of that size. The blue line is the time taken by NumPy itself. The orange line is TensorFlow NumPy running on CPUs, while the red line is TensorFlow NumPy dispatched onto GPUs. The green line is with some compiler optimization on CPU. We'll go into compiler later in the talk. So if you look at these lines, on the left-hand side of the plot, you can see that the times are pretty similar. In fact, NumPy might be running a little faster for very small input sizes. This happens because today NumPy's dispatch latency is much lower, of the order of 1 microsecond. So if your benchmark is dominated by dispatch latency, NumPy does a much better job today. But however, as the problem size grows, so as you move towards the right-hand side of the plot, you see that TensorFlow starts becoming much faster. And towards the right-hand side, which is like about 1 million input size, it is even 7x faster on this toy problem compared to NumPy. And GPU is, of course, much, much faster. So the summary is that you can take existing code and without doing anything extra, if you have GPUs, TensorFlow magically leverages those GPUs and makes a computation much faster. And even on CPUs, you have some advantage because of TensorFlow's highly optimized and multi-threaded kernels. Next, we will talk in a little bit more detail about what is supported versus not, and what flexibility NumPy brings to the users. So we already have support for a large API surface of NumPy. Around 200 API endpoints have already been added. And please check out the API documentation at the link to find out more about what's supported. What's currently not supported in terms of features is, one big one is mutation. So our ND arrays are currently immutable, and this is something that we're going to be working on. Some of the D types like object and rec array are not supported. We also don't support Fortran order of data views Also, like NumPy's API, Python Swig integration is not supported. So having said that, let's dive into some of the flexibility that NumPy brings, even to TensorFlow users. One big feature we believe will be useful is indexing. So NumPy's indexing is pretty powerful. So besides the basic indexing, as shown in this slide, which is using single values, adding new axes, doing ranges and strides, or using ellipses for going over a different number of dimensions. So that is basic indexing. You can also do Boolean indexing, which is one of the indices could be a list of Boolean values. And in this case, for example, the second dimension says true, false, true. And what that means is it will select the first and the third rows on that dimension. It also supports advanced indexing, which means indices can be tensors or sequences. So in this case, we show like second dimension having a tuple and the third dimension having an ND array. And TensorFlow and NumPy defines semantics for how this works. Please check out the NumPy indexing guide for more details. NumPy also brings in flexibility via type promotion, and its type inference is also different than what TensorFlow natively supports today. So for example, NumPy prefers wider types like int64 and float64 for converting literals to ND arrays. Also, you can do things like adding an int64 with a float64, and it will be type promoted to float64. Another powerful feature which is shared with TensorFlow is shape broadcasting. What that means is you can have inputs of different shape being passed to a function or an operator, and NumPy will define semantics for how to broadcast those inputs to a common shape and then applying the operator on it. And the implementation would then leverage that to make it much more optimized instead of actually tiling the values. So again, check out the NumPy broadcasting guide for more details on these features. So with this, we'll talk about interoperation with NumPy itself. So notice I said, like, we support around 200 NumPy API endpoints. However, NumPy defines many more. And so if as a user, you want to leverage other functions that are not currently supported, you can do that. In this example, we show, we start with creating a TensorFlow ND array, and then we pass it to a NumPy function. So notice that we do np.sum, y equal to np.sum, which is calling it to a NumPy function with a TensorFlow ND array. How that works is when the function is called, it will force a conversion from TensorFlow ND array to a NumPy ND array, which might involve copying data. The function is called, and then a NumPy ND array would be returned. Similarly, you can take this ND array now and pass it to a TensorFlow NumPy function. So here we call tnp.sum, and that again triggers conversion from a NumPy value to a TensorFlow value, calls the function and returns a NumPy ND array. So this allows you to kind of take existing code, and even if things are not supported, you can at least get it working. It might not work as well because of all these data copies, but let's at least get your code running. The semantics of the operators are a little bit more complicated. So if you do like x plus y, which is adding a TensorFlow ND array with a NumPy ND array, the semantics are defined by something called array priority. So so you can set this value when you're defining a new class. So in our case, we have defined TensorFlow NumPy with a higher priority. What that means is, in this case, the plus operator will be executed by TensorFlow. And so that will force a conversion from of y to a TensorFlow ND array, and the return value would be a TensorFlow ND array as well. We can also pass TensorFlow ND arrays to other APIs that expect NumPy inputs. So here we show that you can call matplotlib histogram function with a TensorFlow ND array input, and that works again via this conversion to NumPy value seamlessly. All right, so next we'll jump into TensorFlow interoperability. So similar to NumPy, we can also start mixing and matching TensorFlow NumPy functions with TensorFlow functions. So here we import TensorFlow first as STF. We create a NumPy ND array, and then we call a TensorFlow function, tf.sigmoid, on this value. And how that works again is this NumPy ND array is converted to a TensorFlow tensor, and the return value is a TensorFlow tensor as well. This tensor can again be passed to a NumPy function, in this case tnp.sum, and again that does a conversion to an ND array, calls the function, and the output is an ND array as well. Operators similarly depend on the array priority. Currently, TensorFlow tensor has a high array priority, which means the return value in this case would be TensorFlow tensor as well. However, note that compared to NumPy, here we don't trigger any data conversions or data copies. These copies, these classes basically are thin wrappers on each other, so the conversion is zero copy. You can also do the conversion explicitly. So if you have an ND array, you can convert it to a tensor by calling .data property, or we can take a tensor and convert it to NumPy TensorFlow ND array by calling as array. And these conversions, as I said, would happen without copying the underlying data. So next, we'll look at more examples of interoperability by working through an example. So we'll show how you can take NumPy functions and call different TensorFlow functionalities. So we'll start by looking at an input pipeline. So you can call TensorFlow's dataset APIs and then start using that with TensorFlow NumPy functions. So in this case, for example, we pass the random, we create random numbers using NumPy API and then call from tensor slices on that. We also, in the map function, we use the clip function that we have defined on these ND arrays, and all of that works seamlessly and without data copies all over the place. So this functionality is something that users do pretty commonly, where they have input pipelines with NumPy functions, and they believe a lot of these could be converted to TensorFlow NumPy functions and run more efficiently. We'll work through another example where we take this input and then compute a very simple toy model on it, and then compute gradients. This demonstrates how gradients can work seamlessly through both TensorFlow and NumPy functions. So we open our TensorFlow gradient tape scope. This is TensorFlow's mechanism to define what code the gradients are computed through. We do a watch, and I'm not going to details of these APIs. And then you'll notice that in the scope, we now call both TNP and TF functions. So we mix and match these functions. And again, all this works without overheads because the conversion is almost free. And also the gradient node in this case can work through both these NumPy functions as well as TensorFlow functions. So finally, we call tape.gradient, which computes the gradients through all of these function calls and return that. To make it more interesting, we will also show how to compute, for example, gradients and demonstrate TensorFlow's iterative construct. So TensorFlow has both while loops and a higher level function called map function. So how map function works is it takes in a function, it applies it to each row of the input, which is the second argument. So we can use that to compute, in this case, for example, gradients. The way we do that is to take the gradient function we just defined and map it over all the rows of input X. So given this code, now we can write idiomatic Python control flow code. So in this case, we show how to iterate over a data set and compute, for example, gradients for each element for each batch of elements. And then given this, now you can start applying optimizer rules to update your parameters. So this is all great, and we anticipate that this code will be already faster than doing it in NumPy, and also it allows things like automatic gradients through your code. So we also will talk about how to make this code even faster. So one of the tricks you can use is called trace compilation. The way it works is by adding a decorator on any of the functions, it triggers this machinery. What it does is on the first call to this function, we will execute the code, and the underlying machinery will observe what operations are being called. It will take that trace, it will compile it and store it. And on subsequent calls, it will invoke the trace instead of running the Python code imperatively. This gives TensorFlow opportunity for applying different kind of optimizations like operator fusion and so on, which provides a lot of speed up to the code. Another optimization that provides a lot of speed up is auto-vectorization. The way it works is it takes an iterative code and it does a large rewrite on it. So it will take the loop body, it will go over all the operations in the loop body and replace them with operations of higher ranks. And by doing that, it can completely get rid of loops, which provides large amount of speedups. So in this case, replacing map function with a vectorized map triggers this vectorization machinery and can provide large speedups. To show how much speedups we can get, we did again a small benchmark where we varied the batch size and then measured the time taken. And this graph shows input size versus the time taken. So the blue line is the original code with the map function and without compilation. The red plot is with compilation, and the green plot is with both compilation and vectorization. And you can see and notice that the y-axis is on log scale. So notice that as the input size increases, both compilation and vectorization provide huge amounts of speedups. So to summarize, we saw how to take a NumPy code, how to leverage TensorFlow runtime to make it faster on GPUs. We also talked about some of the advantages that TensorFlow brings in, like auto differentiation, compilation, auto vectorization, and so on. Next, Peng is going to talk about how to add new NumPy operations, and then we'll also walk through some case studies of using this API.
Hi, everyone. My name is Peng. I'll take you to peek into under the hood of TF NumPy. And in particular, I'll show you how to add a new operation into TF NumPy. So adding new ops into TF NumPy is the bread and butter of TF NumPy development. The process of adding a new op is basically 4 steps. So when you want to add a new op, you have to read the official NumPy doc for that op to comprehensively understand the behavior of the op. And then you think of a way to implement all the behaviors in Python using TF-ops. So you can look at the folder under NumPy _ops for more information. And we have a comprehensive test suite for NumPy conformance that basically tests all combination of op, shape, and d-types. So we need to run those tests to make sure that we conform to NumPy in all the corner cases, especially d-types, because d-type promotion are where most of the corner cases are. So lastly, this is new compared to NumPy. So NumPy doesn't allow incomplete shapes, but we want to support incomplete shapes to be like more like TF. So there are some tricky aspects of how to handle incomplete shapes. So I will show all this through 3 examples. The first example is like the simplest possible op that we can add. So this is a bare bone op. So as Ashish mentioned, we defined our own ND array class, and it is just a thin wrapper around a TF tensor. So if you are adding an op that directly corresponds to a TF op like cosine, then the work to do is really very simple. You take the TF tensor out of the ND array, and then you give the tensor to the corresponding TF op. And when you get back the result tensor, you apply the wrapper again to turn it back into the ND array, and that's it. So a little more extra here, because we want to accept any array-like arguments, we need to convert that argument into ND array first. And secondly, we have this decorator called npdoc. So this decorator does 2 things. Firstly, it copies the doc string of the original NumPy op, or a link to the doc string, into the doc string of this new Python function. And if you have extra doc string in your new function, it will be appended to the official NumPy doc string. And secondly, this npdoc also does TF export, which export this new symbol under the tf.experimental.numpy namespace. That's our first example. Our second example is a little bit more complicated. well, the only complication is that now we have more than one argument. And as Ashish mentioned before, unlike TF, in TF NumPy, we support D-type promotion. So we have to promote all the related arguments to the common D-type. So we have our own promote D-type utility function, and internally it calls the official NumPy.result type function. So our type promotion rule are exactly the same as NumPy type promotion, D-type promotion rule. So one technical challenge here is that this works for most of the time, but in some corner cases, especially when the arguments are native NumPy types, like native Python types, like Python integers or Python floats. NumPy result type, when it does D-type promotion, it can be value sensitive. It can decide the D-type based on the actual value of the argument. For example, if the argument is Python integer 1, it may choose like a small integer D-type, but if it's like a very large integer, it may choose a larger integer D-type. That is fine in eager mode, but we also support graph mode, the usage within TF function. And in that case, x1 and x2 may be symbolic tensor, so the value is unavailable. So in that case, we really can't do anything. Instead of using the x1, x2, we basically give x1.dtype and x2.dtype to NP result type. So that may result in different type promotion results than NumPy. But those are really just corner cases when x1 and x2 are Python native values. Our last example is for showing the complication of handling of incomplete shapes. So in some of our ops, because of the behavior of official NumPy, we need to, or we want to do totally different computations based on the shape and the rank. So as a simplified Python version, we can just do a Python branching on the shape and the rank. But if we want to support incomplete shapes for the arguments, then there are some challenges. Firstly, when we want to handle incomplete shape, we shouldn't use tensor.shape.rank or tensor.shape. Instead, we should use tf.rank and tf.shape, which will return the shape and rank as a dynamic tensor instead of a static Python value. But then because the shapes are dynamic, then we cannot use Python branching. We need to use tf.count. So that's one requirement that requires to use tf.count. But on the same time, there is another requirement. So if all the shapes of the inputs are already complete, then many NumPy users expect the results to also be complete. So there are two motivations for this. First is that this is what most NumPy users expect. Second is that in one of our use case, which is Trax, Trax actually requires this shape to do this shape calculation in their model initializing phase. So they need to have all the ops used by their model to completely to successfully propagate complete shapes from input to output. So we need to support this. But this raises a problem for TF count because the different branches in our TF count are doing totally different computations. So TF count cannot infer a complete result shape from those different computations, even if all the argument shapes are complete. So in conclusion, we cannot use tf.count in this case. So we have two contradicting requirements. The solution is that we need to constant fold away tf.count. Because we are only dispatching according to shape, and the shapes are already known for all arguments. So actually, the condition in our tf count are already statically known at this time. So we just need to leverage this fact and just eliminate count because the condition is already known. The concrete solution is that we have our own version of tf count, which we call utils.count, that does a tf get static value on its condition to extract the static value, and then pick the true branch or else branch at graph building time. But the problem we find is that the coverage of tf get static value is not very great. It doesn't support many common ops like add or greater or logical or. So when we use those ops, we need to use our own versions of those ops in our condition that more eagerly do constant folding within the op. So like for add, it will do get static value on the two arguments of add, and if both of them are static, then it returns a static Python value. All right, that's all for all of examples for adding a Python op. Then we'll talk about some case studies we have for using TF NumPy. So we'll talk about two case studies. The first is JAX. So there are a lot of existing JAX code written by researchers. So the goal is that we want to try to export those JAX code or JAX library onto TensorFlow for them to enjoy the ecosystem of TensorFlow. But the problem we have is that JAX is not just the TF NumPy. It uses more APIs that's beyond TF NumPy. So our solution is that outside of TF NumPy, we have a TF NumPy extension library that provides a set of JAX-specific APIs. Those APIs include the famous function transformers in JAX like JIT, VGP, VMAP, and some facilities for distributed training like PMAP and PSUM, and also some mathematical functions that's outside of NumPy, like convolution and pooling, and also a set of stateless RNGs that's not part of NumPy. So we successfully done this porting for JAX unit test for NumPy ops, and also the stacks library, which is a very simple layers library within JAX. And we also done it for the neuron tangents model. Our second case study is Trax. Trax is the next generation of tensor to tensor library. So it's a framework for state-of-the-art research for sequence-to-sequence modeling. It's created and maintained by the inventors of transformer, reformer, and many famous NLP models. So it was initially implemented on JAX, but now we have already exported it to TF NumPy, so users of Trax can easily do their Trax training on TensorFlow. So there's a difference between the other porting work. So instead of doing just a one-off porting of the existing Trax code, we actually moved Trax into a multi-backend architecture so that the user can seamlessly switching between JAX backend and TF NumPy backend, and even just the vanilla NumPy backend. So they have very great flexibility when they train their model. So the reason we can achieve this is that Trax only uses a well-defined API surface, and those APIs are supported by both JAX and TF NumPy. So in order to switch backend, there are two ways. You can do it in command line by just giving one extra command line argument, or you can do it more locally within the code and more pragmatically. So in Trax, there is a fast mass module, and the fast mass module have a use backend Python scope manager. So when you open a Python scope using use backend, all the code within that scope will use the backend you specified in use backend. I want to mention we also have a Trax to Keras converter inside Trax, so that you can convert your Trax models into Keras models. And we also support save the model, so you can save your Trax model into save the model, and then later load it into TF ecosystem. So that's all for my talk. So if you want to learn more about TF NumPy, you can follow those links for further reading. Especially, please look at the comprehensive guide we have for TF NumPy. And you can also look at the API documentation for specific documents for each NumPy op. We also have some collabs. So we have one collab that's use a simple multi-layer model to train image classification on MNIST. But it is a distributed training examples. It uses multiple GPUs. We also have a collab that show you how you can use TF NumPy along with Keras and distribution strategy together. Also, there is a Trax collab that shows how you can use Trax, but with the TF NumPy backend. That's all for our TF training talk today. Thank you.